Not the real world, it's kind of the laboratory real world, but I do hope to perhaps make a start towards convincing you that some of the ideas that I'll discuss in this talk are important for getting reinforcement learning algorithms combined with deep neural networks to actually work effectively in complex real world situations. So to start things off a little bit, as I'm sure many of you would agree with me, deep learning is a class of techniques that's proven itself to be really effective for helping us handle unstructured environments, meaning natural, real-world inputs like images from the Emergent dataset, images from all over the web, etc. You can train deep neural nets on large datasets of images or text or speech and so on, and they can recognize things in realistic environments, and that has tremendous value. But of course, if we want to combine this kind of generalization power with the ability to make effective decisions, then we need an algorithmic framework around decision making, which is what reinforcement learning provides us with, right? Reinforcement learning provides a formalism for designing algorithms that make decisions, a formalism for behavior. I probably don't need to summarize it for this audience, but basic idea, you have an agent, it makes decisions, which we call actions. The world responds with the consequences of those decisions, which we call observations and rewards. And we've seen reinforcement learning methods, particularly combined with high-capacity representations like neural networks, succeed in a range of fairly difficult decision-making tasks, from playing backgammon in the 1990s to playing Go in 2016, playing Atari games, etc. But looking at some of these examples of difficult domains in which reinforcement learning algorithms have proven to be very successful, something that really stands out to me is that they look very different from the kinds of domains that I showed on the previous slide. So while one might reasonably say that playing Go is a very challenging decision-making task, its challenge is very different from the challenges in recognizing images on the internet, for example. In particular, all of these domains are essentially closed-world problems. When you're playing the game of Go, you don't have to worry about your opponent spilling coffee on the Go board. That's sort of outside of the closed world in which the agent lives. And the closed world nature of that problem actually removes many of the challenges that we typically think of as being the kind of challenges we want to address with deep learning. So if we'd like effective decision making in open world environments that are not characterized only by requiring a complex chain of decisions, but also characterized by diversity, by a very high variability, things like natural images, then perhaps we need to think a little bit about why we haven't really seen deep RL methods succeed in a really big way in these kinds of domains, and why their successes have perhaps been more limited to these closed world settings. So I'm going to propose one reason for why I believe that to be the case, but there might be others as well. I think that basically what it comes down to is that it's not quite so simple, that deep learning handles unstructured environments like recognizing images on the internet using large and diverse data sets. So how can we possibly hope for RL to enable kind of intelligent machines that act meaningfully in open world settings when we typically study them and train them on data that looks like this, right? So there's a very clear difference between the kind of settings where we do RL experiments and the kind of settings where deep learning tends to excel. And maybe what this kind of suggests is that we kind of perhaps maybe learned the wrong lesson from deep learning. So maybe we took away the lesson that it's about designing algorithms that are scalable enough to train high-capacity function approximators like deep nets. But perhaps the real lesson is that it's about big models and highly varied and diverse data sets. And that second part is really indispensable. And if you remove that, then you end up with methods that work in environments that look like that. So if we accept this premise, then we have to think about, well, what is it that makes it feasible for supervised deep learning methods to be trained on large data sets like that, and why is it that RL doesn't quite get there? So I think that RL has a big problem, and many of you might already guess what that problem is. If you think about supervised machine learning, supervised deep learning, the workflow for building a model looks like this. You go out and you collect data. Actually, typically you don't go out and collect data. Maybe somebody else went out and collected data, so you might just sort of benefit from the fruits of their labor. So you might go out on the internet and download your data. And you do this once, or whoever collected the data did this only once. And the data is there, it's always there for you after that. And then you can train your model on that data as much as you please. And if you want to modify your model, you can modify your model without having to recollect your data, so it's all sitting there for you. And then once you're happy with your model, then you deploy it on your system, on your robot or your autonomous car or your website, and it does its thing. If you want to do reinforcement learning, typically, if we sort of follow the recipe in the reinforcement learning textbooks, it's fundamentally an active learning process, right? You have your agent that interacts with the world. It uses that interaction to update its behavior, its model, or its policy, or its value function, what have you, and then it interacts with the world some more. And it does this many, many times. But now if you imagine that this agent needs to acquire a policy or value function that generalizes over a huge range of different situations, and it has to recollect its experience each time it wants to make a modification to its policy, that means that you're sort of thinking of ImageNet scale, or at least ImageNet level diversity of data being collected every time you go around this loop, or else you need to think of something else. And I think actually this is maybe understating how bad the situation is. Actual reinforcement learning is actually, I think, tougher than this picture might suggest, because actual reinforcement learning has an outer loop. So there's this inner loop where your agent interacts with the world, collects data, and improves itself, which requires collecting highly varied data each time you go around. But then there's this outer loop with this guy. So this is basically all of you, if you're working on reinforcement learning. So when you go in and you modify something about your method, you modify something about your model, then you presumably have to repeat this whole process. And actually, it's this part that in practice ends up being so challenging, because if someone, if you went to somebody who works on, let's say, factory automation, you told them, you will have the most capable robot imaginable if only you let it spend like 3 years doing nothing but collecting data. That's not actually a bad value proposition. The problem is that it's not just that. It's an iterative process. So it's not really that they would only have to spend those 3 years. They would have to modify their method, modify their model, et cetera, and that can become completely intractable. Yes?
Isn't a similar thing happening though in supervised learning all the time, right? Even supervised learning, we happen to have humans in the loop. They change the models. It takes time. Maybe it's just like nobody will learn as much as you want because they just sit in the computer.
Right, yeah. So in supervised learning, you also have humans in the loop. I don't think the problem is... So let me repeat and you can tell me if I said it right. So in supervised learning, don't we have the same problem, because we also have a person going in there and tweaking the model, and then there's this kind of outer loop. Is that?
Yeah.
Okay. So I don't think this is the problem. I mean, I've been this guy, maybe I am still this guy. I have many good friends that are this guy. There's nothing wrong with having a person tweaking the model. I think the problem is that when every time you do this, you have to go around this really, really costly cycle. So when you work on things in simulation, of course, the cycle is not so costly. But if you imagine, let's say, something that we might consider a little silly, using reinforcement learning to train, let's say, an autonomous car, right? That would be an enormous economic investment. If you had to make that investment each time you modify your algorithm a little bit, that would become intractable. With supervised learning, that's not the case, because with supervised learning, you just use all the data you've already got. All right. So, at this point, as many of you might not at all be surprised to hear, I think that the solution, sort of the antidote to this trouble, is to start taking off-policy reinforcement learning even more seriously, and to develop algorithms that are off-policy in a very real sense. I think we've had effective off-policy reinforcement learning algorithms for a while, but I would claim that they're not quite as off-policy as they ought to be, and I'll tell you a little bit about what I mean by that later on in the talk. But at a high level, what I think would be the much more practical, much more useful paradigm for reinforcement learning is one where you have an agent that has interacted with the world before. So this is sort of the analog of your ImageNet data set, where you have a large data set from past interactions. You have a method that can use that large data set of past interactions to train up a model, a policy, or a value function for as many epochs as you want to reach some baseline level of competence. And then, of course, for many tasks, there will be some edge cases and some additional little bits of situations that don't quite, that are not quite represented in your big prior data set. So in those cases, you might want to go back out into the world and collect a little bit more data as necessary to patch up those holes. But when you do that, you of course add that to your big data set, so that if in the outer loop you want to change your model, you don't have to go and do this all over again. And I think if we develop good algorithms and also good experimental frameworks for working in this regime, it'll make it much more practical to get deep reinforcement learning algorithms out there into the real world. All right, so at a very high level, how does off-policy reinforcement learning work? Well, at the risk of making a somewhat controversial statement, I think off-policy reinforcement learning, there are many ways to instantiate it, but they all boil down to some form of prediction. The question is, what is it that you're trying to predict? So if you predict future observations, you're essentially training your model to understand how the world works. This is what we would call model-based reinforcement learning. And if you're predicting future rewards, you're understanding the consequences of your actions, and this would be things like dynamic programming algorithms or Q-learning. And I would actually say that they're not as different as they might first appear on the surface. So towards the end of my talk, I hope to elaborate on this point a little bit, which is actually going to raise some concepts that are a little bit similar to what John mentioned in his talk, although not in the context of exploration necessarily. So here's what I'm going to discuss as far as the technical methods. I'll talk about off-policy model-free reinforcement learning algorithms. Then I'll talk about off-policy model-based reinforcement learning algorithms and discuss maybe some empirical results that get us thinking about the difference between these two. And then I'll tell you about why I think they're actually not all that different and why they're, in some sense, a little bit of the same thing. But let's start with model-free reinforcement learning algorithms. So in this part of the talk, I'll sort of first provide some good news and then maybe some not so good news. So the good news that I'll discuss is that actually fairly simple, well-known ideas that have been known for several decades do actually work in the real world, and we can make them work in an off-policy regime. And then I'll tell you why, in some cases, they actually definitely don't work in the off-policy regime and how we can get started fixing that. So first will be the more empirical good news, and then sort of the more conceptual bad news. So let's start with the good news. So first, just to get everybody on the same page, this is going to be things that many of you might already know, but we're going to be operating in this regime where we have our off-policy data set. We do some training on that off-policy data set, occasionally go out and get more data. Our data consists of tuples, SAS prime. We're going to be training our policy or our value function using the task reward. And a very useful tool for doing that is something called the Q function. So your reinforcement learning objective is to maximize expected reward. The Q function, these are fairly standard definitions, just tells you the expected reward that you will get if you start in a particular state and take a particular action and then follow your policy. The great thing about the Q function, of course, is that once you have one, you can recover a policy that is as good or better than the one that you used to get that Q function, simply by being greedy, by taking an action with probability 1 if it maximizes that Q function. And you can, of course, recover the optimal Q function, meaning the Q function for the optimal policy, by enforcing the Bellman equation for your states and actions. So if you can somehow get this equality statement to be true, then you will have Q star, and then you will have a good policy. So this, of course, suggests one of the most popular classes of off-policy reinforcement learning algorithms, which is Q-learning or fit-a-Q iteration, which amounts to just trying to enforce this equation on a data set of transitions. So that's what we're going to work with. We're going to start with this. We're going to try it out in this kind of regime. We'll see how well it does, and then we'll talk about how, in some cases, it might not do so well. All right, so we don't need on-policy data to do this. That's the good news, because this equation uses a transition SAS prime. The only place where it accounts for your policy is, of course, in this max, where it maximizes over the next action. And there, it's using your function approximator to essentially answer this counterfactual query: how well would I do if I were to take a different action, namely A prime? The transition itself, the SA part, can come from any policy. So the practical instantiation of this is that you collect a data set using some policy, could be a variety of different choices, add it to your giant buffer of data, and then you have an inner loop where you sample a little batch from that buffer. You minimize the difference between the left-hand side and the right-hand side of that Bellman equation, and then you repeat this, and then occasionally go out and collect more data. So it sort of suggests this asynchronous parallelized view of reinforcement learning where you have the world, you interact with it, pull in these transition tuples, you have your big bucket of transitions, you're crunching away on all those transitions, training up your Q function, and perhaps in parallel you have another process that goes out and grabs more data. So we can try to instantiate this at kind of a larger scale with some real-world robotic systems. So we did this at this point about a year ago at Google, where we set up a large number of robots. And these robots are tasked, in this case, they're tasked with grasping objects. That was the particular problem that we picked. And they're collecting data, and we have all of their past data, all the data they collected in all previous experiences. So this is the kind of experiment that takes several months to run, sitting there on the disk. And as this is all happening, we load in off-policy data from all the stored data we had before. Live data coming in from the robots gets put into an on-policy buffer and also stored back to disk for later use. And then we have to enforce this Bellman equation on all of our data. So this we're going to break down into two parts. We're going to need to calculate this right-hand side, and we need to actually perform the minimization. So the right-hand side is calculated by a set of what we call Bellman updater jobs. So these are a bunch of jobs that crawl over this buffer, and they just calculate that max. Calculating that max is a little non-trivial in the robotics setting because, of course, these are continuous action problems. So there's a little stochastic optimization that happens there with kind of a gradient-free method that calculates that max, and it pushes labeled data back into the buffer. So the labeled data now has the right-hand side calculated, which is what I'm referring here as QT, and the state and the action. And then there's a separate set of training threads which pull in those label tuples and actually train the Q function. So this is kind of a systems architectural level view of this thing. But at a high level, you can think of this as basically a highly parallelized, large-scale instantiation of everybody's favorite Q-learning method. So we set this up and we asked it to do grasping. Grasping is a very simple task to define for in this setting. We simply give the robot a reward of +1 if it picks up the object, which is easy to check. And then we trained it on about 1,000 training objects with about 600,000 training grasp attempts. And we ended up using a fairly large neural network for the Q function. It had about 1.2 million parameters. It's large by reinforcement learning standards. Computer vision researchers would probably chuckle at this a little bit because by computer vision standards it's actually tiny. But you know, for RL this is a pretty big network. And of course, the interesting thing to me was the fact that it could operate in this regime where it's loading up large amounts of data from past experience, but also from kind of the robotics side of my work. I was quite interested to see what kind of interesting behaviors it would come up with. And to me, the interesting thing was that some of the strategies he came up with really don't look very much like traditional robotic grasping systems, right? Traditional robotic grasping systems tend to be very geometric in nature. They select an appropriate grasp point, servo to that grasp point, and pick up the object, whereas this kind of method ends up with a policy that's a lot more reactive, so you can go in and you can perturb it, you can push objects around, and it will try to react and re-grasp and correct its behavior. It works under a variety of conditions with novel objects, in dense clutter, with objects that are transparent, and so on, yes?
Just a question regarding the video.
Mm-hmm.
The motion doesn't seem to be super smooth, like
yeah.
human would be reaching a smooth spot.
Yeah.
So why is that?
Right, so something that some of you might have noticed is that it is a little bit jerky, right? Every time it pauses like that, what's actually happening is that it's making a new decision. So the Q function, so the Q function gives you the Q value for a state and action, but you have to actually pick that action. And it's not thinking and moving at the same time. It first moves, then thinks. You can make it think and move at the same time, but then actually the scheme breaks. There's a fix that we have for that we've developed since then that I can tell you about offline. All right. And then for something a little bit more empirical, in case you sort of don't like the videos, we did test it on a data set of new objects. It had a grasp success rate of 96%, which for a robotic grasping system, grasping from monocular RGB images is actually quite good. The 4% of the failures were on this octopus. So if you don't have octopuses that you need to grasp, this is actually a decent method to try to employ. But, so that was kind of the good news. Now, I promised I would get to the bad news. And the bad news is this, that I motivated all this stuff by saying, well, we'd like to collect a past data set of past interactions, train on it for many epochs, and occasionally go out and collect more data. And you might think, well, okay, we've got this prototype. It seems to suggest that the recipe basically works. Why do we need to do research on this? Well, the catch is that it's not occasionally. So remember that in that system diagram, I had the robots collecting all this data live as the training was happening. And that might at first seem like an implementation detail, but it turns out to be quite important. So it's not actually occasion, it's repeatedly getting more data. And you take a hit if you don't do this. So we can run that whole system in fully off-policy mode. We can basically take all the data collected from all the experiments, including the experiments that got us to that 96% success number, train on that, and we'll get a success of about 87%. Now, you might think, okay, 9%, what's the big deal? But if you flip that around, 4% error versus 13% error, that's a huge difference, right? So that's more than a 3x increase in the number of mistakes that the robot is making. And it's not because of the composition of the data. It's actually the fact that new data from your actual current policy is being injected back into the data set. So that should be a little worrying to us. So what's the problem? Why is fully off-policy learning seemingly so tricky? So let's think about this recipe a little bit more. This is the equation that I had before for you. And the interesting bit, of course, is the target value, this max over a prime of q s prime a prime. Now, your q function in the fully off-policy setting is trained on your buffer. And we can represent that buffer with a distribution. We'll say that actually when you sample from your buffer, you're sampling from some underlying distribution that I'm going to call beta. So beta SA is the probability of SA under the whole ensemble of your behavior policies. So what action will be selected when you perform this max over A prime? Well, let's say that these are some actions I've seen. This is, of course, a cartoon illustration because every action will be in a different state, but pretend that for some reason I visited the same exact state exactly 3 times and I saw these 3 samples. Now you might look at this and say, oh, okay, easy. I know what the function is. It's this thing, right? So when you do the max, clearly you should get this peak. But unfortunately for us, large high-capacity function approximators are a lot more creative than this. So they will give you a curve like this near your samples, but they'll also give you fun things like that, far away from your samples. In fact, far away from your samples, you can get all sorts of interesting behavior. And of course, when you're performing this maximization, that maximization is unaware of where your data was sitting, so it's going to very happily grab this peak over here because it's larger. So when you take the argmax of your Q function, the A star that gives you that argmax, if that makes beta of S comma A star small, that action is not to be trusted. That is not actually a good action. It's simply an action that is fooling your Q function into thinking it is good. And of course, the larger your action space, the more complex your problem, the more likely you are to have your Q function be full of holes like this, full of seemingly good actions ready to be exploited by your unscrupulous target value optimizer. And of course, because in Q learning you then take this value and then you back it up through your whole system, you end up training on garbage, not just on that one state where you got that nasty action, but on all the states preceding it, because now they're backing up this garbage value. And this is actually a really big problem. So how do you get Q learning style algorithms to stop training on garbage? Well, first let's modify the equation a little bit to make it a little more general. So the target value before was max over A prime. Now I'll rewrite it as the expectation with respect to A prime distributed according to some policy pi nu. So the classic version of this is just pi nu is the greedy policy, but we can make other choices for pi nu and see what that does. So then we can say that, well, we're going to try to fix this problem by changing our choice of pi nu. What is a good choice of pi nu that might address this issue? Well, one option that you might consider is to keep pi nu close to beta. Because if beta is the distribution of your data, then if your pi nu is close to your data, then it will say, okay, don't do this stuff, do things that are closer to these nice points. So you could, for example, say, well, let's constrain the KL divergence between pi nu and beta. KL divergences are very convenient to work with. That's a reasonable starting point. This has 2 issues. One issue is fairly easy to fix, but the other issue is rather problematic. So the easy issue is that we typically don't know beta. But you can patch this up. You can, let's say, fit another function approximator to beta or something. So this is probably not the biggest issue. The other issue is much more severe, which is, I can illustrate in this curve. So this is a plot that Avral Kumar, the student who was working on this problem, made. This is the Walker 2D benchmark task from the OpenAI Gym Suite. He collected random data, and then he used that random data buffer to do fully off-policy training. The green line shows regular reinforcement learning, and it doesn't do so well, so 200 is not a very good score on this task. The red line is actually what happens if you just do imitation learning on that data. So that's essentially behavior cloning a random policy. So this is basically a baseline. Regular reinforcement learning, this kind of reinforcement learning with the distributional constraint, you can't see it very well. It's the blue line. It starts off over here and then drops. So it actually ends up doing quite poorly on this. Why does it do poorly? Well, because the constraint is essentially telling it to stay close to a random policy. A random policy is not a very good policy, so if you try to stay close to a random policy, you're not going to do very well. But intuitively, you don't need to stay close to the random policy. You need to be sort of inside of it, right? So inside this big high support region, you need to be somewhere within like a subset. So this is way too conservative. If you simply constrain the distributions, you will avoid taking out of distribution actions, but you'll end up with a very bad policy if your buffer was collected using bad policies. So what you can do is you can instead constrain to the support of beta. So if you can somehow figure out that this is the region where your buffer has high support, you can only trust the values inside that region. And there are a variety of different ways to try to approximate the support. The particular approach that we used, and that's this orange line, was to use maximum mean discrepancy between your data distribution and the policy pi. There are other techniques you could use too to constrain support, but essentially this allows your policy to not actually match the entire behavior policy, but to sort of match a little subset of it. And that ends up being very important to get good behavior, especially when the behavior policy is bad. All right, so let's look at the performance of these things on some mediocre data sets. So this is all fully off-policy training, meaning that the data was collected using some scheme. In this case, it was sort of a partially trained policy from another RL run, and then used to train up a number of policies using a number of different methods. So the dotted pink line shows the average reward in the data set for each of these experiments. The blue line shows this kind of distribution matching approach with the constraint that tries to stay close to the behavior policy. Then the orange line is our method, which does a support matching, and the green line is naive reinforcement learning. So you can see that in these cases, sometimes you have good data, and then behavior, just like the naive behavior cloning baseline is pretty good, in which case our method does about the same. In some cases, the data is bad, the naive behavior cloning baseline is bad, and the distribution matching approach tends to be pretty similar to that. But if you match the support, then you can actually improve on that. All right. So maybe the takeaway from this part of the talk is that off-policy reinforcement learning can work on large data sets, but it's not truly off-policy because you have to keep crunching away on collecting additional data using your latest policy. But we can actually identify the issue that's causing the trouble there and potentially have a little bit of a fix for it. I don't think this is the complete solution to all issues with off-policy reinforcement learning. In fact, we can actually construct data sets using mixtures of policies where all these methods will break down horribly. So there are still many open problems here. And I think this is actually a really fruitful area to explore in the future. But what I want to tell you about a little bit for the remainder of the talk is how we can also do off-policy learning using model-based RL methods, and a little bit about how these model-based methods relate to model-free methods. All right, so for model-based reinforcement learning, actually the algorithms portion of this will be very simple. Here I want to actually focus a little bit more on some of the empirical observations. But at a very high level, the idea is a little bit similar to what we had before. We're going to have a data set that we collected, maybe from past interactions. The data set consists of transitions. And now what we're going to train on that data set is not a value function, but a model that predicts the probability of reaching the next state given the current state in action. And that's a supervised learning problem. So that's, you basically use your favorite supervised learning method as a subroutine. Our favorite supervised learning method is to use deep learning. So this is going to be stochastic gradient descent on a big neural net. And then occasionally go out and again collect more data. Now, there are a few things about this that are quite nice. It's a comparatively simple supervised learning problem in the inner loop here. It's natural and straightforward to apply to multitask settings because you can learn one model for multiple different tasks. If, let's say all of your tasks are situated in the same physical universe, they are all governed by the same laws of physics. If you learn those laws of physics, you can presumably use them to do a variety of different things, and that's quite nice. So models can be repurposed to new tasks, potentially even without any additional learning. So if you've got a really good model, you could even just use it straight away to do something new. The issue that's often cited as kind of the downside of these kinds of approaches is that they're typically worse in terms of final performance than model-free RL. And this is actually the question that I want to try to study a little bit. Is this always true? Typically, the reason that's cited for this is that, well, model-free RL actually optimizes for the performance on the task. Model-based RL optimizes for the accuracy of a model, which is sort of an indirect proxy to that. So the algorithm that I'm going to show you is actually a very simple algorithm. So you have your agent collected some experience. You're going to use that experience to train your model with supervised learning. And then you're just going to use that model to plan. So there's actually no policy learning, no value function learning here. We're just training up a model, and then we're just planning through that model. We're going to plan with a stochastic search method in this case. So the planning problem amounts to finding the argmax for a sequence of actions that maximizes the expected value of the reward, where the expectation is taken under the model that is learned. And then you repeat this process. Now, there are a few details here that matter, so you have to choose the right class of function approximators for this probability distribution. It turns out that good uncertainty quantification ends up being kind of important. In the particular method that I'll show, we use bootstrap ensembles for uncertainty estimation, so we have an ensemble of neural nets. There are other ways to do it too. Choosing a good optimization method over here also matters. The particular one that we use is a derivative-free optimization method. You can think of it as a variant of the cross-entropy method. Again, there are other choices, potentially even better choices for this. And the details do matter for setting this up properly, which are covered in this paper. But what I want to focus on more is the performance of this method in comparison to model-free reinforcement learning techniques. So we studied this approach in the context of dexterous manipulation tasks where you have a robotic hand that needs to manipulate objects. And we wanted to try to understand when should we prefer model-based RL over model-free RL. So one of the things that's maybe in agreement with commonly held intuition is that on narrow tasks, like if you have a single thing that you want the agent to do, model-free RL tends to do very well. So my student, Anusha Nagabandi, who was doing this research, set up a task where a robotic hand needed to write a digit on a piece of paper. So if it has to write one digit, it has to just like write a 0, just draw a little circle. Here are some learning curves. Let me explain what these are showing. The green line is this model-based method, kind of its most capable instantiation. The blue line is soft actor critic, which is an off-policy actor critic algorithm that is model-free. The red line is natural policy gradient, so it's an on-policy policy gradient approach. And you can see that they all do pretty well. So this dotted black line is the best you can do on this task. The model-based approach is faster, which is kind of in agreement with what we would expect, but they all reach good final performance. However, if you have a broad and diverse range of tasks, model-based RL actually tends to have a little bit of an advantage. Why is that? Well, because the model is the same model for all the tasks, right? In this case, we're going to be writing different digits, as you might have guessed, on this piece of paper. The way that the pencil is held in the hand and the way that the physics of this task work don't change based on which digit you're writing, but the policy might actually need to change pretty drastically. So here are some animations of this hand writing different digits with model-based RL, and it's the same model used for all of them. The target trajectory of the tip of the pen is the input that's provided as context to get it to do the right thing. And when we look at the behavior of this method in that setting, this little green bit here, that's actually the model-based method, so it actually learns very quickly. That's why it takes up such a small part of the plot. The model-free methods do make progress, but they end up actually doing substantially worse on this task. I think that there remains to be done a lot of analysis as to why model-free RL in the multitask setting is difficult, but empirically it does seem to be substantially harder in many cases. Now, of course, there are a few caveats that are to be mentioned in regard to these results. The task is constructed in such a way that it is somewhat easy for model-based reinforcement learning, right? One of the shortcomings of the approach that I sketched out is that because it's relying on this planner, it's not going to do that well with long horizon tasks where the errors in the model accumulate. This task is set up as a somewhat short horizon task because that little green dot, which tells you where to put the tip of the pen, provides fairly dense supervision. You still have to figure out how to actually move the whole hand to do this, but you don't have to reason about extremely temporally extended behavior. So it's testing out your ability to represent complex behavior, but not necessarily your ability to solve extremely temporally extended problems. All right, now another example where we might prefer model-based RL, when we want to transfer the same dynamics model to perform multiple tasks. So perhaps we have a model that we trained while getting a robotic hand to rotate these two spheres in the hand. We can actually take that same model without any additional learning and use it to optimize a different reward function. So this reward function is now saying, do this behavior, but do it clockwise instead of counterclockwise. It doesn't do it quite as perfectly, but is still able to repurpose that model. Of course, you can't do this with a policy because a policy is optimized for a particular task. You can also use that same exact model to move the ball to different locations in the palm. And of course, the more conventional, kind of better known benefit of model-based RL is the sample efficiency. And you can learn these tasks in a few hours of interaction. So this is what Anusha ended up doing for the real-world hardware experiments. So this is a real-world robotic hand learning in the real world entirely from scratch to perform that rotation task from before. And of course, it's quite bad in the beginning, so 0.5 to 1 hour into the training process, it drops them quite a few times, but after a few hours, it gets better and better at this. In the span of about 2 hours, it can make one turn pretty consistently. In the span of 4 hours, I think the success rate goes up to about 85%. So this is, a pretty efficient method for learning in the real world that can incorporate, of course, off-policy data for model learning. All right. So the last thing I want to tell you about, and I unfortunately don't have kind of nice, flashy robot results for this, but hopefully the story will be somewhat interesting, is that these model-based RL methods are maybe in some ways not all that different from model-free RL methods. And what I want to tell you about in this part of the talk is how Q functions can in fact also learn models. So far when I talked about models, I said that, well, they're sort of a different kind of creature. They're trained with supervised learning. They're trying to predict the next state. Q functions are trained with this dynamic programming method. But actually, they're not all that different. So to see how they might not be all that different, let's set up a simple little problem that we can use to understand this. I'm going to have my agent start in this green location, and he's trying to reach this orange location. And I'm going to try to get him to go to many different places. So I don't want just a policy that goes to one place. I want a policy that knows how to go to any place. And the target location, the goal, is going to be given as an additional input. So my Q function is a function of S, A, and G, where G is the target location where I want the agent to go. So that's pretty straightforward to do. Just plug in G everywhere, and you can train an agent that goes everywhere. So we can do this with off-policy Q learning. Same recipe as before. We collect data, sample from our buffer, et cetera, et cetera. But one of the things we can recognize looking at this algorithm is that there's something special about that goal. The goal that we picked while we were collecting the data is actually kind of irrelevant to us when we're using the data for off-policy learning. So we could modify this method to say, don't even bother storing the goal that you used when you collected the data. Instead, sample these batches from your buffer, sample a goal from some other distribution. As long as you can calculate your reward function for this new goal, you can just sample all the goals you want. You don't actually care what goal was actually being attempted while the data was collected. You can relabel your data with new goals. Okay, fairly simple idea. I'm not actually sure who introduced this idea. The earliest paper I could find was actually a paper by Leslie Cabling called Learning to Reach Goals. More recently, this was mentioned in a paper that I think someone brought up in the previous talk called Hindsight Experience Replay. It's sort of an idea that reappears again and again every few years. Yeah, basically the idea is that you take your data and you relabel it with different goals that you could have been attempting. And of course, that means that each transition in your buffer can be reused multiple times. So you can kind of harvest more knowledge from it. The interesting thing about this scheme is that if you're a little careful with your choice of P of G, you can get much faster learning from doing this. Faster in the sense that you can get much more sample-efficient learning. Now, one might wonder, why is this the case? Well, my hypothesis is that the reason that's the case is that by using the same transition to teach your Q function about different goals, you're in effect putting knowledge into your Q function about the model. So if you tell it, well, this thing is reaching this goal, not reaching this one, and not reaching that one, you're essentially telling it what the difference between those goals is and teaching about reachability in your system. And that's not actually a vague intuition. We can actually make this a little bit more precise by showing how you can extract that model out of the Q function. So we're going to make one more small modification. There are a variety of different ways to do it, but this one is probably the simplest. We're going to add one more input, which is the horizon. So I'm going to input this additional variable tau, and tau just counts down every single transition. And when tau hits 0, you're at the end of your horizon. And we'll choose the following form for our goal condition reward. We'll say that the reward is 0 if tau is greater than 0, and then at the end, once tau gets down to 0, your reward is the negative distance between your state and the goal. So essentially, you're trying to reach this goal, at the end you're some distance away, and your Q function is answering the question, if I'm trying to reach G in tau steps, how close will I get to it? So that's what your Q function is trying to learn. And you can, of course, relabel with all the G's in the world and train this for a long time with many, many gradient steps on the same data. And this thing is a model, and you can actually use it like a model. So let me tell you a couple of ways that you could use this as a model. Some of them might seem a little silly, but some of them are, I think, kind of interesting. So one very silly way to use this as a model is to do constrained optimization. So if I'm doing constrained optimization for trajectory optimization for planning, I want to maximize my total reward along my trajectory with respect to my states and actions. Now, of course, if I just do this, I'm going to end up with some silly states that don't actually obey the dynamics, so I have to add a constraint to this, which is that, st plus 1 has to be equal to the dynamics function f applied to st and at. And that's exactly what my Q function can tell me. So if I just impose the constraint that Q of st, at, st plus 1, comma 1 is equal to 0, this constraint says that when you take action at in state st, your distance to st plus 1 will be 0 after one step. So enforcing this constraint basically enforces that the sequence of states is dynamically consistent for a deterministic system, of course. You can extend these ideas to stochastic systems too, but that's quite a bit harder to write. So for deterministic systems, we can do it like that. Now, this is a little silly because you're only using the horizon of 1, so arguably you're not getting any benefit out of the dynamic programming when you do this. But you can then immediately say, well, okay, what if we don't use a horizon of 1? What if we impose a constraint that says st, at, st plus k, comma k is equal to 0, and plan over every kth state? Now you have something that's actually kind of new, something interesting. You're planning, but you're not planning every single time step, you're planning over segments of time. And these segments of time can be quite long. So now you actually have a hierarchical planning method that's using your Q function as a multi-time step model. So before, we were maybe planning one step at a time. You want to ride your bicycle from UC Berkeley, where I work, to San Francisco. You plan one step at a time, every single movement of your muscles. That's going to take quite a lot of effort to plan. But if you plan over longer segments, you might figure out that, maybe first you have to go over here, then you have to cross the bridge, go over here, then go over there. So being able to plan at coarser temporal abstraction can be extremely beneficial, and this can in principle allow you to do that. All right. So I'm a bit low on time, so I'll summarize the results briefly. The first thing, of course, that you can get out of this is you can get much more efficient learning if you don't care about temporally extended tasks. But perhaps the more interesting thing that you can get out of this kind of scheme is you can actually use it for trajectory optimization. Now, there's a little bit of a challenge when you try to plan with these kind of approach, which is that you are optimizing over state variables, which ordinarily wouldn't be a problem in optimal control if you had the true model, but because your constraint is actually a learned object, you want to again be very careful to make sure that your optimizer doesn't come up with out-of-distribution states that will fool your Q function to thinking that they are reachable. And this tends to be a big problem if you have states that are infeasible. So if you have a simple navigation task going from the blue dot to the green dot, the model might understand that the green dot can't be reached by going through the wall, but it might not produce a reasonable answer if you ask it how reachable a location inside the wall is, because it was never trained on that. So you want to be very careful when you use this for planning to avoid allowing the optimizer to query your Q function with invalid states, because those are also out-of-distribution states. So to present the main idea here very briefly, what you actually need to do if you want to use this for planning is build a space where you know the set of valid states and you only optimize over valid states, which you can do by, for example, training a generative model on all of your valid states. So here we're planning over images. Of course, if you optimize over image pixels, you get a bunch of garbage images that fool your Q function. But if you learn a latent variable model with some latent space, let's call it Z, and then you optimize over that latent space where you know that every location is a valid state, then you can actually prevent this thing from exploiting out of distribution actions and actually do temporally extended planning over Z in this case, over image observations. So the main idea there is your latent variable model, which could be something like a variational autoencoder, provides a state abstraction that is suitable for planning, and this Q function, that what we call the temporal difference model, provides a temporal abstraction to plan over longer time segments. Now, of course, there are many details that aren't covered here that matter a great deal, like how do you turn this into an unconstrained optimization, how do you optimize it, etc. So I, of course, won't have a chance to go into that. But at a high level, this thing does basically work. So this is an illustration of the little 2D navigation task from before. The red dots show the sub-goals that are produced by the planner. So the lighter colored one is the first one, the darker colored one is the last one. And this bottom row shows the sub-goals in the latent space where, of course, all latent points are valid. And it works for a little robotic manipulation task where you have to reach out and move an object using images, and for a little navigation task where you get images of the navigation scene. And of course, the more complex the task is, the more temporally extended it is, the more benefit you derive from planning. All right, so at this point I'm going to wrap up. I'll unfortunately have to skip this, but I'll be happy to take any questions. Thank you very much.